All right, everybody. Test-like question with mechanisms on it. We have to do a mechanism that accounts for all four products. And then we're going to circle the two major products formed. You guys got any hints based on our previous activity? Which two solve a lot of problems? First one still has this little guy here. So does this one. I don't like it. This has a lot less. What are the two types of strain? Because you're going to be using those in your description. When you go to ring size 5 from ring size 4, what two things improved drastically? Angle strain went down a lot because your angles are now almost perfect. They used to be close to 90 degrees. And what's the other one called? Torsional strain. Now torsion, that's a weird strain. I don't like the way they named it. It's descriptive, but it's awkward. Torsion is just an action. Like in mechanical engineering, this would be torsion, when you twist an object, okay? Now what cyclobutane wants to do is twist to get away from all that eclipsing, right? It wants to sigma rotate, so H's aren't in front of each other, they're like on an angle to each other. It can't do that, the ring size is too rigid. So because of that restricted rotation, they call it torsional strain. You've restricted how much torsion you can do. It's not a terrible name. I kind of like it, but it's kind of not a direct name, right? It's really an eclipsing strain. That's a direct name. If you wrote eclipsing strain, I might consider giving you full credit, okay? It's just called torsional strain. Both your mechanisms next Monday. First step is the same. Pi electrons attack what? No matter what, next Monday. Your first arrow, the pi electrons will attack what? She said the least electronegative. She's not wrong. We're going to be more obvious because you don't have many mechanisms yet. You have only mechanisms with strong acids and alkenes. The first step in both mechanisms, no matter which one you're looking at, is attack the strong acids H. Yes, it's a less electronegative H, so I can't say what you said was wrong. It's just, I want you to really focus. You're only looking for the strong acid. Where is it? Where is it in this one? HCl. Pi electrons attack the H. And what's the second arrow look like? From the bond to Cl, nicely said, very concise. Becomes a lone pair, doesn't it? Automatically draw two carbocations. There's an alkene. It has two carbons that are double bonded to each other, right? Cation number 1 has the cation on one carbon and the H on the other. Cation number 2, you flip those. So here's your arrow. Here's your cation number 1. I'll just put it on the top. And you make that, and I think you'll probably make a little more of this one originally because it's tertiary. But tertiary is not the end-all be-all. We can do a little better than tertiary. I'm moving that up there. When you made each product, you made a chloride plus Cl minus. Yeah. You have to show a lone pair if you need to use it in a mechanism. Her question was, do we have to show the lone pairs? I only need to see a lone pair if you use it in a mechanism. And that's why there's only one lone pair on my Cl instead of 4. Yes, there are 4, or those aren't Cl. Those aren't chloride with an IDE at the end. All right, now I do see one of the products immediately. I'm going to go get my points for it. You see the first product? Where the Cl is? Isn't that on this carbon? They will make a bond and make that product, and we will be done with the first product. Notice that arrow goes all the way to the carbon atom. Does one of the products result from Cl minus attacking the other C plus? I think it's the second product, isn't it? Let's do it. So we're done? Oh, heck no, you're throwing away a lot of points. I got to make product 3 and 4. Okay. Do you agree both of those products involved expansion of the cyclobutane? You have to agree. There's no cyclobutane in them. Okay. All right. Now I'm going to give you a big tip. I'm going to say it twice. It's so important. Which of these cations is a candidate for a rearrangement? A cation is a candidate for a rearrangement if it's adjacent to a branched carbon. Okay? Now you could argue this is a candidate for a rearrangement because it's adjacent to this. But you would be wasting your time because the other cation you've already drawn, right? If you moved an H from here up there, you'd get this cation, but you're not going to do that. You get that cation directly from protonating this pi bond and putting an H on the top. You get a cation in the bottom. What I want to look at is right here. Isn't this a branched carbon adjacent to the cation? Right there. That's branched. How do you know it's branched? It's got more than one bond to carbon. That's a candidate for rearrangement using this bond or this bond. This is a candidate for rearrangement only with an H on the next one over. Don't do that. You've already got the cation that results from that. You made it direct. Okay, so what I don't want to see is what I'm about to write. You put your pencil down. Do not write this down. Some students think they can save time by doing stuff like this. They'll say, oh, I know how to do that rearrangement. This thing breaks and goes there. Now what you're saying is, I'm having the Cl minus attack this carbon and I'm rearranging it. Ladies and gentlemen, you're going to get 5 bonds to your carbon, and 2 things never happen at once, ever. That's not reality. 1 thing happens at a time. If you need this carbocation to rearrange, you need a second copy of it. Think about it this way. Say I made 1 million of these. Maybe 100,000 reacted this way. I still have 900,000 to react, right? So I need another copy. You copy it. Do not be lazy. You copy it. And I know I need 2 copies because I can do the rearrangement 2 different ways. Take a look at your previous document. We saw this one. And from the same cation, we saw a different one. We saw this one. Remember, you're allowed to rearrange any of the 3 bonds from this carbon. You could move the H, which wouldn't get you anywhere. You would still have cyclobutane. You can move this bond or this bond. And the results are different. Once again, I'm going to put some labels because this is our first time seeing this stuff. In pink, we'll go A, B, C, D, E. A, B, C, D, E. And it looks like I broke A, D in the first one, so there's B to C. And we got our labels, pink E, A, B, C, D. D is now bonded where? What atom is D bonded to now? To say, I need a letter. E, yeah. And the cation is on the atom that lost a bond and didn't replace it, A. I like picking A for the new cation, don't I? And let's draw what we get down here. You got your cyclohexane didn't change. You got your E to A didn't change. Your A to D to C to B didn't change. And you have a new bond. Need letters. Light pink. A, B, C, D. E. What's the new bond again this time? What letters? B to E. And A is a cation again. Different cation than before. And then one of these makes product 3. That's this one. How do I know? How do I know this one gives the third product? Take a look. It's got A, one away from the bridgehead. And that's going to be where the Cl goes because that's where the plus is. That's that one. And it goes BC and then D with a methyl. BC, D with a methyl. Good. What about this guy? I got to see both on the screen. Here's my new guy. Oh, definitely. Look, bridgehead goes to a C that's a plus that will be C with a Cl. Goes to a C with a methyl. Goes to a C with a methyl. Goes to CB. CB goes back to the bridgehead. So tell me how this one becomes the fourth product. Product 4. And this one becomes product 3. Yeah, let's do that. Those arrows are getting too big. Why we have an eraser? Change color. My apologies. Trying to think the best way to get to product 3 without disrupting things too much. There. How do I make those products? What do I need? I need Cl minus, right? You just draw another copy of Cl minus. You have as many as you need, everybody. Another copy of Cl minus down here. Attacks the C that has the plus. Attacks the C that has the plus. All the way to the C, please. And there you go. And I don't like how messy that looked up at the end. So just redoing it to make it neater. We had a hot pink A, a light pink A. That was A. And the arrow went all the way to the carbon. There we go. Not quite done. Both these cations, that's this one and this one, I need the magic words. Have best national parks to visit. Have reduced. What are the magic words? They're pretty new for us. Angle and torsional strain, exactly. Okay. That's my explanation for B, I think. I'm trying. My computer is not doing anything. Hang in there. Still not letting me write. Let's see. I hope. Nope, that's C. The circle was B. Here we go again. All right. And that's that.